All right, welcome back to the last lesson of Unit 4. Fantastic news is one of the hardest things in this lesson is actually pronouncing the name of the lesson, which is Stochastic Processes. It sounds like it might be confusing. It actually is not too bad. It's pretty much making a tree diagram and putting percentages on it, or putting probabilities on it. Pretty straightforward, not too difficult. So rather than try to explain that how to do it, we're going to jump into some examples. And you'll notice there's not even really a definition of stochastic processes. A stochastic process is actually a little bit tricky to define in words that make sense to human beings. It's one of those weird mathematical things, but essentially it's a chain of events where any given event changes the outcome of some future event, possibly a little, possibly not at all. Um, but we're going to kind of see this in the tree diagrams that we draw. So let's start off with one that we've done before, where we're just going to look at the probability of getting two heads if we flip a coin 3 times. Now I'm going to start off by drawing it exactly the same way that we would have drawn it back in unit, whenever we were doing this, unit 2, I think, when we started doing tree diagrams. I believe. Anyway, let's just see what happens. So remember the tree diagram. We're going to start at a point, and then each branching is going to represent one possible thing that happens, or one thing that needs to be answered. So in this case, we're flipping a coin 3 times. So I'm just going to make a little note here. This is first, second, and third flip. And we're going to branch once. So the first flip can be a head or a tail. The second flip can be a head or a tail. And then the third flip can be a head or a tail. I'm going to try and fit these all in somewhat nicely. Okay, so the way that we can do that is we can say, okay, the probability of getting two heads. Well, if I look at it, there are 8 possible outcomes. And there are, how many of them have, now it says getting two heads. It doesn't say exactly or at least. I'm going to assume it means exactly. And if the question doesn't specify, make your best assumption or ask. But in this case, I will try on evaluations to make sure that I'm as specific as possible. So how many of them have exactly 2 heads? And that would be, I believe, this one, which is head, head, tail. This one, which is head, tail, head. And then the bottom one, tail, head, head, is there. So there's 3 of those. And 3 out of 8, I think, is 37.5%. Okay, so that's how we would have approached this back in Unit 2. To do this as a stochastic process diagram, what we're going to do is actually add the probability of each thing happening on the lines, on the branches of the tree. So, for instance, our first coin flip, there was a 50% chance of being a head and a 50% chance of being a tail. I'm going to write these as decimals, and you'll see why after I've done a couple. So this is just representing that there's a 50% chance of following the head branch, and there's a 50% chance of following the tail branch. And then these are all going to be 50% chances because they're independent events, nothing special. And the outcome here is a little bit boring because all of these events are completely independent of each other. But the idea is that if I want to calculate the way of getting from the starting point over here to the end of any given 3 choices, I just follow the lines there and then add up multiply the percents of those happening. So for instance, the first one, head, head, tail, if I follow the path head, head, tail, what I could do is multiply the numbers along that path. So 0.5 times 0.5 times 0.5, and that's going to be 0.125. Now this one, again, pretty boring because every path is going to be a 0.5 times a 0.5 times a 0.5. So that path will also be that one, and this will also be that. And by the way, I could do this for every path, but I can also just do it for the ones that matter to me. I don't need to know the probability of getting 3 heads because it has nothing to do with the question. There's no point in doing the calculation if I don't need the answer. And then if I look at those and I add those 3 possibilities up, they're 0.375, which is 37.5%. Same answer as I got before, and there's no reason in this particular question to do the stochastic process diagram the way that I did. I could have just done a regular tree diagram or solved it some other method. The reason that this one is so boring and not needed is because every outcome is 50-50, which is exactly what we made the assumption back at the beginning, where all outcomes were equally likely. Now, where this comes in handy is when the outcomes are not equally likely or the outcomes change based on what's happening within the problem. So let's go to question 2 and talk about Oscar the nervous test writer. There's a lot of information here. Try not to get overwhelmed by it. It just gives you a set of instructions on how this thing works. I'm also not sure why it would be true. It's a fairly fictitious question, but let's go with it. Okay, so Oscar's a nervous test writer. He figures that if he gets a question right on the test, how he knows that, I don't know, he has an 80% chance of getting the next question right as well, because he's confident. But if he gets it wrong, there's only a 40% chance of getting the next question right, because he's now nervous because he's blowing the test. He's writing a test that has 3 questions on it. I know you guys just dream of the test that only has 3 questions. If he has a 70% chance of getting the first question correct, what is the probability that he'll get perfect or at least pass? So those are the 2 scenarios we're going to look at. Okay, so there's 3 questions in this one. And we're going to use the same diagram, by the way, for both of part A and part B. So I'm just going to leave a little bit of space there and say, okay, he's got 3 questions. Question 1, question 2, question 3. So now his first question, he can either get correct or incorrect or right or wrong. The word that we use to describe these doesn't really matter, but choose something so you can put down a letter that makes sense. I'll just use right and wrong. And then his second question could be right or wrong. And his last question could be right or wrong. Okay, now's where we have to be a little bit careful because unlike our coin question, I mean, the diagram so far looks exactly like the coin question, except with R's and W's instead of H's and T's. But now the probabilities are all different. So I can't just say probability of getting perfect is 1 out of 8 because there's not a 1 in 8 chance that he's going to get all 3 questions right. It doesn't work out that way because there's a whole bunch of stuff going on. What we are told, though, is that the first question, he has a 70% chance of getting right. So 0.7 0.7 or 70% chance of getting it right means that he has a 30% chance of getting it wrong. And by the way, now I think you probably understand why I'm using decimals instead of percentages. It's just easier to multiply them. And now I have to go back and double check the instructions. The instructions say that when he gets a question right, the probability the next one is right is 80%. If he gets it wrong, the probability the next one is right is 40%. So working my way up, if he got the first question right, there's an 80% chance he'll get it right and a 20% chance he'll get it wrong. But if I go down and got it wrong the first time, there's only a 40% chance he gets it right, meaning there's a 60% chance he gets it wrong. And then I follow that same logic through all of these. Top one there is right, so he gets another 80-20 split. If he gets it wrong, it's a 40-60 split. Right, 80-20. Wrong, 40-60. Okay, so the first one that we want to take a look at is the probability he gets perfect. Well, that would be this path right here. And all I have to do, and I could write, actually I will write these out, I guess. It's going to be 0.7, 0.8, 0.8. Those are the 3 numbers along the path of right, right, right. So 0.7 times 0.8 times 0.8. So there's actually a 44.8% chance that he gets all three questions correct. That's pretty good. All right, now we want to look at the scenario where he gets at least 2 out of 3 right. So that would be the scenario we've already done counts. So does this one. He gets 2 right and the third one wrong. Here he gets the 2 right with the middle one wrong, and here he gets 2 right with the first one wrong. So now we have those 4 scenarios. Now those ones are not going to necessarily be equally likely because of the way things worked out. So that one's going to be 0.7, 0.8, 0.2. This one is going to be 0.7, 0.2, 0.4. And this one is going to be 0.3, 0.4, 0.8. And I'm just going to work out those individual percentages once I get my dogs to start barking. Give me one moment. Okay, I think they're stopped for now. We'll see how long that lasts. The second line is 0.7 times 0.8 times 0.2, which is 11.2%. The next one is 0.7 times 0.2 times 0.4, which is 5.6%. And the last one is 0.3 times 0.4 times 0.8, which is 9.6%. Okay, so those are all possible outcomes. Oh, I guess I can write down up here the answer to the first one is 44.8%. And then for passing, at least 2 out of 3 correct, I just add those up. So 44.8 plus 11.2 plus 5.6 plus 9.6 is 71.2%. So a pretty significant chance that Oscar is going to at least pass his test, and a decent chance he's going to get perfect on it. Oh well, can't win them all. Okay, so now this one, I will point out that we could also have approached this one indirectly. However, for the part A, indirectly would have been calculating 7 of those 8 outcomes, which seems kind of silly. And for part B, I would have been calculating the 4 that I didn't calculate, which is the same number of things to calculate. So indirectly in this case, I don't think saves us any time. But we could have done that. Question 3. This question's actually been inspired by my girlfriend, who has 4 nephews, all of which are, well, obviously all of which are boys since they're nephews. But her brother has 4 kids, all of them are boys. And they looked into the stats of that because they were like, she wanted a girl so badly, but no, they got a 4th boy. And apparently that after you've had a certain number of children of the same gender, they tend to end up being the same again, at least the same birth gender. So they're actually, I'm making up the numbers for this question just because working with weird, very in specific numbers is just messy. But we'll say that for the first child is a 50-50% chance. After that, there's a 60% chance it'll be the same gender as the previous child. So again, I'm going to point out that this has no real no real scientific basis to those numbers. I mean, we usually assume it's 50-50 for boy girl. That's not even technically correct. It's close, but it's not exact. And then the 60% chance, this is completely made up for this question. Please do not take this to your science class and tell them that Mr. Ray, your math teacher, told you that that was biologically correct. It is not. We just need math problems. Okay, so same idea as we did last time. We have a first child, a second child, and a third child. So our first child, and again, we can choose male, female, boy, girl, whatever you want. So let's do male, female. And we could have done, in fact, I think we did do a couple questions like this back in Unit 2, where we We assumed everything was 50-50 and always would be. And so we only need to calculate basically, how many outcomes were what we wanted, how many outcomes were their total, and just do simple probability. In this one, we're going to do 50-50 for the first child. However, for the second child, it's going to be a 60% chance to the same as the first. So male would be 60% male, 40% female, and female would be 60% female, 40% male. And then again, follow that pattern through. If it's the same, it's 60. If it's different, it's 40. Now that one, I realize it looks like I did 60-40 again. And that's just because female was 40. Oh, sorry. No, I did mess that one up. I want to be careful on these. Female should be 60% chance of the next one being female as well. Male is 60. Female is 60. Okay, we have all those scenarios. So if there's 3 children, what's the probability that we have at least one child of each gender? So here we have male, male, female, male, female, male, male, female, 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 male, male, female, male, female, 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 male. Okay, so we have 6 scenarios that we could look at there. Those are 6 that meet our criteria. Now, in this case, 6 of the things are the things we're looking for. There's only 2 that aren't what we're looking for. So I think what I'm going to do is I'm going to point out that those 2 are not the scenarios we want. I just calculate them, especially because they're actually kind of nice. The first one is 0.5 times 0.6 times 0.6, or 0.5 times 0.6 squared, if you want to shorten it a little bit. And that's going to be 18%. And the last one actually is the exact same. Okay, and if I add those together, I get 36%, which is basically saying there's a 36% chance I will not get the outcome that's desired, which is at least one of each gender. So what I can say is that for my final answer, I can take all possible outcomes, which is 100% likely, subtract off the probability I get an outcome I don't want, and I get a 64% chance that I'll have at least one child of each gender. Now, there's absolutely no reason you couldn't have gone through and calculated the 6 direct ones. You'd get the same answer. It just takes a little bit longer because it's 6 calculations instead of 2. All right, let's take a look at question 4. There is a 40% chance that it will rain on Friday. If it rains on any given day, it is 10% less likely to rain on the next day because, there's less moisture in the air. If it doesn't rain, it's 20% more likely to rain the next day because the moisture is building up. Or at least that's my theory. What is the probability that it will rain at least once on the weekend, Saturday or Sunday? So now, again, I'm going to point out that this is a math problem for math class. There is no scientific basis for this question whatsoever, besides my really weak logic that I just pointed out. So we're not going to actually take this to a meteorologist and say, I can now predict weather accurately because Mr. Ray told us the equation. It doesn't work that way. But we have a nice problem that we can work with. So let's do our tree diagram again, our stochastic process diagram again. In this case, our 3 possible branches or outcomes are Friday, Saturday, and Sunday, or our 3 choices, I guess I should say. And each day it's either going to rain or not. So Friday it'll rain or not. And again, the letters you choose here don't matter as long as they're descriptive enough to you that you can keep track of them. Rain not. And okay, rain not, rain not, rain not. Perfect. Now we go back and follow the instructions that are given to us. So the first event that happens is Friday's rain event, and it says at the beginning of the question, there's a 40% chance it will rain on Friday. So 0.4, and then obviously 0.6. Now, this is where we've got to be careful because this is going to keep changing our percentages all the way through. If it rains on a given day, it is 10% less likely to rain. Okay, so if it rained on our first day, then the probability it will rain the next day is 10% less than the 40% it was for Friday. So this drops from 40% to 30%, meaning this is 70. And I'm actually going to just fill out the top right one as well. If it was a 30% chance and it rained, there's now only a 20% chance it will rain on Sunday, and an 80% chance that it will not. Now, please be careful on this next step because students tend to bugger this one up every possible time. If it doesn't rain, it is 20% more likely to rain the next day. So if I'm trying to figure out, let me just change colors here so I can kind of show you what I'm doing. If I'm trying to figure out this one, what's that probability going to be? Because this is the one that people always mess up, or the equivalent of it in a few other places. There's actually this one and this one are the students, or the ones students tend to mess up. Okay, so the probability of it raining is 20% more likely than it was the day before. And a whole bunch of people want to put 0.8 because this is 0.6. But 0.6 is not the possibility of it raining, it's the possibility that it didn't. The possibility that it rained is up here, 40%. So if it didn't rain, it is now a 60% chance of raining and a 40% chance of not raining. And similarly, going down, if it was 60% chance of raining on Saturday and it didn't, there is now an 80% chance that it will rain on Sunday and a 20% chance that it will not. Okay, so we still have a couple little branches to fill in. The top one, or the second top one on the right, the day before, there was a 30% chance that it would rain. It did not, so it increases by 20% to go up to 50. And then the last one, there was a 60% chance of raining. It did, so it goes down by 10% to 50. And I think we've got all the numbers on our diagram that we want. So now what we're looking for is all the places where it rained at least once on the weekend. So it rained at least once on the weekend here. Here it rained Saturday but not Sunday. Here it rained Sunday but not Saturday. Here it rained both Saturday but not Sunday, Sunday but not Saturday. So there are 6 possible scenarios there that we could do, and we can work all of them out. Or we could do it like the last one and say, here's a day where it didn't rain either day. Here's a day where it didn't rain either day on the weekend. Whether or not it rained on Friday, by the way, is irrelevant. The question is just about Saturday and Sunday. So rather than calculate the 6 ones and add them together, I'm going to calculate 2 of them, add them together, and then subtract it from 100. So this first one here is going to be 0.4, 0.7, 0.5. And this one's going to be 0.6, 0.4, 0.2. And just to save myself a little bit of room, because I want some space to write on the right-hand side there, 0.4 times 0.5 times 0.7. I think I could do that in my head, but I'm also thinking I could screw it up. So that's 14%. 0.6 times 0.4 times 0.2 is 4.8%. So if I add those together, 14 plus 4.8 is an 18.8% of no rain. So 100 minus that is 81.2% chance that it will rain at least once on Saturday and Sunday anyway. Again, Friday's rain does not matter. So your choice, calculate it directly or indirectly, but either way you should get the right answer. So do be careful. Those three that I highlighted tend to be the ones that students mess up because they're looking at the wrong number in the last outcome. So they always want to look to the number that's, for instance, for this one here, they want to use this number because it's on the way there, but that's not the number that you're looking at. You want to always look at the number, in this case, the probability that was raining that previous day. Okay, one more to finish this off. And one thing I'm going to point out here before we get started is it looks like I should have left a lot more room than I did. This one is a special question, and you'll see why in a second. So Homer goes to Moe's and orders a beer. For those who don't know, Homer goes to Moe's bar quite often in The Simpsons and drinks quite a bit of beer. Um, After the first one, he's 90% likely to order another, and for each additional beer he drinks, he's 10% less likely to order another. What is the probability that he stops after his fifth beer? Okay, so I'm going to make a little list here. He's got his first beer, his second beer, third, fourth, fifth, and then we'll see what happens from there. Again, I'm kind of foreshadowing because I know what the answer looks like, but let's start off with he drinks 5 beers, or maybe he doesn't. Okay, so from our starting point, he has two options, or does he? He could drink a beer or not drink a beer. Now, in this case, I can put this down as drink or not drink. However, really, if you read carefully, I don't need to put that end branch because it says Homer goes into Moe's and orders a beer, which means this is a 100% chance and that's a 0% chance. He definitely does it, meaning we don't actually need the second row of the N. Now, probability he drinks a beer, he's either going to drink a beer or not. There's a 90% chance he will drink a second beer and a 10% chance he won't. Now, I don't need to actually branch the didn't drink his first beer because it never happened. And similarly, when I go to the third beer, I can say he drinks or doesn't drink, not drinks. If he does, it's 10% less likely, and that means it's 20% that he won't have a third beer. Now, I don't have to branch the N from the second beer because if he didn't drink a second beer, he can't possibly have a third. Think about that. If I say he walked into a bar and he had a first beer and a third beer, but no second beer, well, then the third beer is the second beer. So we don't have to branch the no drinking branches because they don't happen. They don't continue. They're a dead end. And similarly, we can do this with fourth beer, drinks or not drinks, fifth beer, drinks or not drinks. And this keeps going down by 10%. So 80 goes to 70, 70 goes to 60. Now, actually, we do have to put a sixth beer on here, not because he drinks it, but because we're asked what the probability is he stops after the fifth beer, which means he does have a fifth beer, but then we still need to see whether he stops or drinks a sixth. So he drinks or does not drink. This would be a 0.5. Oh, I should put these ones on here. They're all going to be numbers that add up to 1. And the path that we want is that he drinks 5 beers and then stops after that. So there's no sixth beer. So we have DDD, DDN is our actual chain there. And if we want to put those together, I'm going to write below just because there's a little bit more room. To get along that path, it's 1 times 0.9 times 0.8 times 0.7 times 0.6. And then it's 0.5, but just to be clear, it's not the 0.5 drink, it's the 0.5 not drink. Okay, when I put that into my calculator, 1 times 0.9 times 0.8 times 0.8. I'm going to have to try and get this in without making any errors. 0.9 times 0. Calculator problem. Okay, 0.9 times 0.8 times 0.7 times 0.6 times 0.5 equals 0.1512 or 15.1%. Now, does that seem like a fairly low percentage chance of happening? Uh, yeah, kinda. But keep in mind that there's a whole bunch of possible scenarios here. He could stop after his first beer, or his second, or his third, or his fourth, or his eighth, or his 23rd, or his 115th. Um, Actually, that's not entirely true because I think what happens after a few more beers is that there's a 0% chance on the top. In fact, it will be a 0% chance on the top if we follow this pattern. And then he has a 100% chance of not drinking any more beer. But I think that's his 10th beer. So it's not a super likely outcome, but it is actually a reasonable outcome. Okay, so sometimes premeditating what the tree diagram is going to look like can save you a little bit of time and space when you're designing it. And here's an example of one that it doesn't branch constantly everywhere. Only one branch in each choice actually continues to branch. One of them's a dead end, and that significantly shortens it. It actually makes the problem almost linear. Okay, so hopefully I didn't confuse you too much with that. Try some of the questions. Again, if all outcomes are equally likely, then you can go back to Unit 2 way of solving type things, or at least earlier probability way of solving things with regular tree diagrams. But when probabilities change or are not equally likely, we may want to use this method. So the next time I see you will be in our final unit, Unit 5, which we're going to continue on with probability distributions, which is going to be a fairly good recap of Unit 4 with a little bit of addition to it. We're going to tighten up our notation a little bit, and we're going to talk about some fairly common types of probabilities that actually do occur. All right. Good luck, and we'll see you next time.